Hello guys, in this tutorial I will show you how to make this animation in geometry nodes. First of all, I want to say that I made this inspired by the tutorial of dynamic outlines made by Entagma. The link to that video is in the description. I decided to make a tutorial about this because the only problem with that video is that was made before geometry nodes started to use fields. So almost every node in that video don't exist anymore. I will start by showing the complete node tree. With this configuration, you can change the size of the plane, the width and height of the waves, the resolution of the effect, and the offset that can be used to make the animation. First, add a grid. Connect size X and size Y to group input. Add two inputs to group input node. The first one will be render resolution, and the second one viewport resolution. Both of them type integer, default 10, minimum 2, and maximum 1000. Add a switch node. Change input type to integer, connect render resolution to false and viewport resolution to true. Add an isViewport node, connect it to the switch node, and connect the switch output to vertices X and vertices Y. Connect the grid to a set position node, add a combine XYZ node, and connect it to offset. Make a new collection. Add the objects you want to create the waves to this collection. In geometry nodes, add a collection info node, connect it to a realized instance node, and then to a geometry proximity node. Connect the instance value to the C input of the combined XYZ node, add a position node, and connect it to source position. We will use the distance value to control the effect. Add a math node, change the operation to cosine, multiply the distance value before the cosine node to change the width, use an addition node to change the offset, and multiply the value after the cosine node to change the height. Use the distance value to create a falloff. Multiply it with negative values. Use an addition node to control some of the initial falloff. Use another addition node to combine the waves and the falloff, and activate the clamp to transform every negative value to 0. Add a group input node to control the width, the offset, and the height. I multiplied the width and offset by 10 just because I like to use small numbers to control them. Add a set shape smooth node and a set material node. In the material, add a geometry node. Connect the position output to a separate XYZ node. Connect the Z output to a math node with multiply operation and a color ramp connected to base color. Choose the colors you want in the color ramp and change the roughness to 0.2. Well, this is the end of the quick explanation. But if you are like me, if you see what I see, if you feel as I feel, and if you will seek as I seek, then it means that you want to know how all of this works. So I will explain everything in more detail. I use a grid to control the amount of vertices that the plane will have, because this effect uses them for pretty much everything. That's why the more vertices we use, the smoother everything will look. The switch node output a different value depending if the boolean value is true or false. The isViewport node always output a boolean with the value of true when you are using Blender in a normal way, but output a false value when you press render image or render animation. So this way we pre-visualize the animation with low resolution and render the result with high resolution. We use a set position node with combined XYZ node to only change the vertical position of every vertex. We use the collection info node so we can use multiple objects at the same time in our effect. The only thing we need to do is put every object in the same collection and use a realize instance node. The position node outputs the position of every vertex in our grid. The geometry proximity node finds the closest point to the source position in the target geometry and outputs the distance between those two points. To explain the wave effect, I will show you a simple example to make it more clear. I'll use a plane as a target and a 10 by 1 grid. If we connect the distance value directly to the combined XYZ node, we see that the vertices go from 0 to 10 in the z-axis. This is because the face of the target is in the same position that the closest vertices, and is 10 units away from the farthest vertices. Then we use a math node with the cosine operation. This output values from 1 to -1 in an infinite loop, which transforms our grid into a simple wave. A simple explanation about the cosine and sine operation is that they output the x and y values of the position of a point that is being rotated in a circle with a radius of 1. If you want a better explanation about this, I will leave a link to a video in the description. When we multiply the values before the cosine operation, this is the same as scaling the wave horizontally. When we add values before the cosine operation, this is the same as moving the wave horizontally. And when we multiply after the cosine operation, this is the same as scaling the wave vertically. If we only want to show part of the wave, we can clamp the values after the wave effect with a math node. This keeps everything between 0 and 1, and if you want more control, you can use a clamp node. To show the falloff effect, I will disable the clamp for now. We already know that using the distance value will make the vertices go up in the z-axis. So if we want our wave to go up as well, we only have to add the distance value to the final result of the wave effect. We can control the falloff with a multiplication and an addition operation before we add it to the wave effect. And now when we activate the clamp, it makes it look as if the wave is disappearing the further away is from the target geometry. Well, this is the end of the tutorial. Leave a like if you like it, and subscribe to know when I upload the next one. Take care and see you later.